Hello and welcome to All Space Considered, everybody. Tonight is the third Thursday of the month, and usually we have our show tonight, and tonight we do. Tonight, I want to make sure that we mention that All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, and the City of Los Angeles. And as always, we like to thank our exclusive nonprofit partner, Griffith Observatory Foundation. Tonight, we have a really interesting show. First of all, I'm going to start off with some brief astronomy bulletins. I've just got a couple of little stories to get things rolling. And then we have a very special guest, Dr. Gabriele Valiente. He's Italian, so I'm working on my Italian here. We had some folks in our back office that were actually practicing. But anyway, I don't see her here yet, so I can't call on her. But make sure you let our foundation folks in if they're trying to get in the theater. And he's, by the way, the deputy head of system science and engineering at LIGO Caltech. And if you don't know what LIGO is, it's an instrument that can detect gravitational waves, literally the vibration of the universe. Super, super cutting edge science, and it's really very, very interesting things. I really love it. Well, anyway, I'm going to kick off the program tonight with just a little bit of science. What you're looking at here, this image, is an image of the globular cluster Omega Centauri. It is it's a very massive globular cluster. It's in our own Milky Way galaxy. In fact, some folks think this might be the leftover core of a dwarf galaxy that was sort of disrupted by the tides of our own galaxy. Our own galaxy puts tides on things that are orbiting it and can strip off stars as this object goes around. Well, over a very long period of time, much of this little dwarf galaxy may have been stripped away, leaving this inner bulge. Well, we thought if that's the case, maybe there should be a black hole in there. We often find black holes, objects that are so massive, even light can't escape, in the center of galaxies. Well, people had looked before and they hadn't found it. Well, finally, some astronomers using the Gemini telescope in the southern hemisphere, where you can see Omega Cen down in Chile, they were able to measure the speeds of the stars using a spectrograph, and they saw some stars that were just going too fast. Moving so fast, they're saying, well, we need a black hole to hold them in position. There's no reason for these things to be moving that quickly. And they think the black hole has a mass of about 8,200 times the mass of our sun. So now you might think, why does that matter? Well, black holes can come in kind of two sizes, we find them. White dwarfs are little tiny things. They're not black holes. They're made when a star like the sun dies. Neutron stars, a slightly more massive star than our sun, can make a neutron star. Well, a star that's maybe 1820 solar masses, when it dies, it can make a black hole. And it'll be a 3-4 solar mass black hole that'll get left behind. Well, those are called stellar mass black holes, or sort of star-sized ones. They have the mass of a star. Well, then we also find supermassive black holes in the center of galaxies. The center of our galaxy has a 4 million mass black hole down in the center. Pretty massive. We find black holes that are even more massive, tens of millions, hundreds of millions in bigger and bigger galaxies. But where are the ones in between? We're not really sure where these supermassive ones come from. We thought, well, maybe you need to merge smaller ones, the stellar ones, together and build it bigger and bigger and bigger. But you'd need like 1 million of them to make our 4 million solar mass black hole in the center of our galaxy, and we're not seeing them. So folks, myself included, have been looking for these. There's hints of them places. There were a paper by a colleague of mine, Mike Rich, and I think Carl Gebhardt and Lewis Ho found one in the globular cluster G1 in Andromeda, hint that it might be there, but it wasn't conclusive. Well, anyway, so that's why we're excited by this recent result that they're seeing these stars that are indicating there must be a black hole there that's 8,000 solar masses. That falls right in the center of this range in between. So we're seeing signs there is one. That's pretty cool. Now, also, there was another study that came out right now. This is a cluster of stars near the center of the black hole in our galaxy. So that thing labeled Sagittarius SGRA with a star there, we call it Sag-A star. That's the location of our 4 million solar mass black hole. Well, this cluster shouldn't be there. That black hole should throw these stars all over the place. They should be disintegrating. This cluster should be flying apart, and it's not. So some people went and studied it, measured the motions of them, and they're just not moving fast enough. They're not evaporating, as we call it, as the things float away. So there must be a black hole in the center of this too. And this black hole's around 800 solar masses. So these two studies that have found intermediate mass black holes right in a row just within this last month, pretty cool. Now, we have found some evidence for them before. In fact, the strongest evidence we had for an intermediate mass black hole was from the LIGO telescope. Virgo's another gravitational wave astronomy telescope observatory. But LIGO-Virgo black hole mergers, LIGO saw one that's called GW190521, catchy name. But when those two merged, one had a mass of something like 65 solar masses. The other was over 80. I think it was 82, if I remember right. And when they merged, they made a black hole of 142 solar masses. You can only make about 65 solar masses in a stellar mass black hole. So LIGO saw evidence for two intermediate mass black holes, really. The one that was 85 was probably really intermediate mass, and then these two merged to form another one. So LIGO, the instrument that our guest speaker is going to tell us about tonight, actually found an intermediate mass black hole as well, although this was back in, I think, oh gosh, I want to say 2017 or
2019.
18. 2019, okay, is when the publication came out.
19 there is for 2019.
Yeah. So anyway, I'd like to welcome our guest right now to tell us all about LIGO. So welcome, Gabriella. Thank you so much. Everybody welcome our guest. And thank you so much for joining us tonight.
Well, thank you, David, thank you for the invitation. Thank you for the perfect introduction to the topic of the talk. And thank you, everybody, for coming. And this was a perfect introduction because tonight I want to tell you a story. I want to tell you a story about stars, about black holes, about gravitational waves, and the instruments and the people that made the discovery and the detection of gravitational waves possible. So this story starts with a star, actually maybe two stars, stars that died because the nuclear fuel at the center of the star was exhausted. There was nothing that kept the star stable as our sun. And so gravity won over everything, and gravity had the star collapse. Everything collapsed into the core of the star, a big explosion, a supernova happened, and then at the end, what was left, nothing could stop gravity for crashing everything down to a single point, forming what we call a black hole. It's what remains at the end of the death of a star that is big enough that nothing can stop gravity. There were actually two such stars, and those two stars formed two black holes. Were those stars already orbiting around each other at the beginning, and then they both became supernova and formed two black holes? We don't know. Maybe the two stars were just wandering around in a globular cluster. They formed black holes and then captured each other. What we know is that a long time ago, about more than 1 billion years ago, those two black holes got closer and closer and closer. As they got closer, they were deforming space and time. Gravity was so strong to create deformation of space and time itself. And as they were moving around each other, those deformations were changing, were dynamic. There were ripples that moved away in space and time. As those two black holes were moving around each other, they would emit more and more gravitational waves, shedding out more and more energy. And so they were falling into each other, moving faster and faster and faster until they collided and formed one single bigger black hole. So what was going on? Sorry, it's a little bit dark, but you will see later. So as the two black holes were getting closer and closer, they would move faster and faster, and they would deform space and time more and more. And so you can see some shade of greens here moving away and becoming stronger and stronger and stronger. That's a simulation of the deformation of space and time. Those gravitational waves, as we call them, ripples in space and time, that travel away, and then the two black holes collided, and a final burst of gravitational waves was emitted. Think like what happens when you throw a stone in a pond, and you have those ripples on the surface moving away. The two black holes were the little stone, and we're sitting at the edge of the pond, about 1.5 billion light years away, waiting for those gravitational waves to travel across all the universe, take their time, they move at the speed of light, the fastest that anything can move, and they finally crossed Earth. And when they crossed Earth, something like this happened. So gravitational waves deform space and time. So the distance between objects is really changed. This is, don't worry, nothing like this really happened. This is a vastly exaggerated effect. But a gravitational wave coming through Earth will make things squeeze and shake, something like that. So our goal was to build instruments able to detect this kind of effect. The problem is that the effect was really small. so small that over the 4-kilometer size of our detectors, about 2.5 miles, to actually see that change, we would have to, if this is a hydrogen atom, we would have to zoom into the core, the nucleus of the atom. That's a proton, keep zooming in, and the change of distance over 4 kilometers, 2.5 miles, is this big. So about 1,000th of the size of a proton. So before you call me crazy and you said that nothing like this can ever be detected, trust me for a little bit. Later on, I'll explain you how we actually managed to build instruments that can do this. But the way we physicists like to look at these kind of things is with graphs, because physicists love graphs. So what you see here are the top panel is the observation of the very first event in gravitational waves from our observatory called Hanford, which is in Washington State. And then we have our other observatory, which is called LIVESTREAM, which is in Louisiana. We have in 2 observatories, almost the 2 corners of the United States. So the x horizontal axis shows time passing. And you'll notice that all this plot is about 2/10 of a second. So it was a very fast event. And then you see at the beginning there's a little bit, on the left there's a little bit of wiggles that are just the background noise of our detector, but then there's that clear oscillation building up. And you see 2 things there. It's getting bigger, bigger, and bigger in amplitude, higher and higher, because the 2 black holes are getting closer and closer and deforming space and time more and more. But as they get closer, they also move faster. And so you notice that the peak, the maximum of those oscillations, they get closer and closer in time. This means that the frequency, the pitch, if you want, of the signal is increasing over time because the 2 black holes are falling close to each other. Then at the end, they collide, and there's one final burst of gravitational waves, and then the final black holes just will sit there, maybe waiting for another friend to collide later on, but we don't know. We'll see. So this signal has a treasure of information in it. By looking at the shape of the signal, what we call the waveform, we can really learn a lot. And the reason we can learn a lot is because this guy called Albert Einstein, maybe you've never heard that name before because it's not that very famous, but more than 100 years ago, understood how gravity works and gave us what is called the general theory of relativity, which is, as of today, still the best way to explain how gravity works. And so this theory tells us exactly what is the shape of the signal we should see here. And that depends on how far the 2 black holes were and how big they are. So you see in blue here, again, it's the signal from our detectors. And in yellow, it's a prediction with some random numbers from the theory. It's kind of wrong. But as we change the distance, we move the 2 black holes closer in the universe, you see we can increase the amplitude, so we can match the amplitude. As we change the mass of the 2 black holes, we can actually make the frequency, the pitch, just match. And so by doing that, we can actually really, only from the shape of the signal, know that those were 2 black holes that were about 420 megaparsecs away. That's about 1.4 billion light years. It's pretty far. They collided 1.4 billion years ago, because again, gravitational waves travel at the speed of light. And the total mass of those 2 black holes was about 65 times the mass of our sun. So what's remarkable is that about 3 times the mass of our sun in this collision was completely converted into energy. Picture 3 times our sun disappear in 1/10 of a second and be converted completely into gravitational waves. During that time, the power emitted by this system in gravitational waves outshine all the light emitted by the rest of the visible universe. So that was a pretty catastrophic and gigantic event, one of the strongest events ever detected in any astronomical phenomenon. So you can imagine that this was a very important discovery, the very first time we detected gravitational waves. So not only we proved that the gravitational wave do exist, and we proved that directly, we also proved that black holes can exist orbiting around each other, and they actually behave exactly as Einstein predicted more than 100 years ago. This was the last missing piece to experimentally confirm that the general theory of relativity is working remarkably well. There aren't that many other physical theories that lasted that long. If this was exciting, and this happened back in 2015, something even more exciting happened 2 years later. So David already explained early that when stars die, if they're really big, they can form a black hole. If they're like our sun, they will form a white dwarf, kind of a boring, cold star, nothing happened, will sit there forever. In between, if the star is big enough but not too big, when gravity tries to smash down the star because there aren't nuclear reactions anymore that keep the star in balance, then all the electrons in the atoms will be squeezed inside the nuclei of the atom. They will merge with the protons and they will form neutrons. All the mass of the sun is squeezed down in a ball of neutrons. Picture something which is almost 1.5 times the mass of our sun in a single ball, which is 10 miles in radius. So the density of that thing means that a teaspoon of that matter is about as heavy as Mount Everest. So we had neutron stars. And again, you can imagine we have 2 neutron stars that were, sorry about that. I don't know what's happening here. Technical difficulties, as always. Yes. So the 2 neutron stars, again, the remnants of 2 dead stars were orbiting one around each other. And as they were orbiting one around each other, they generate those ripples in space-time, gravitational waves again. Those gravitational waves were traveling everywhere. But what makes this different from the 2 black holes is that those are not black holes. They're not black. They're big balls of neutron, big chunk of matter. So when they collided, they created a gigantic nuclear explosion. So we expect that a lot of other kind of radiation, electromagnetic radiation, like gamma ray, very strong form of light, and then other forms of radiation would be emitted. And so once we discovered that, almost all astronomers in the world jump into their telescopes, well, not quite into their telescope, they jump to their telescopes and try to look at the patch of sky that we told them where to look and try to find the observation, try to find something new. At the same time, the Fermi satellite, which is a satellite in orbit around Earth, was able to detect a flash of gamma rays. Gamma rays are emitted when you have big nuclear explosions, right? So what they saw, what Fermi saw, it's called a short gamma ray burst. And for the first time, we could prove an idea that we had for several decades now, that those short gamma ray bursts were actually coming from the collision of 2 neutron stars. But the key here is that with the LIGO observation, we were able to point precisely in the sky where the 2 black holes were. And eventually, astronomers managed to see a new dot, not quite a star, but a new light there where there was none sometime before, like in a few days before that. And after that, even the Hubble Space Telescope jumped into the game, because the Hubble being a space telescope always jump into the game. And the funny story here is that at the time we were keeping the discovery secret because we want to, make sure that everything is correct. Turns out that the observing schedule of the Hubble Space Telescope is public, so all of you can go and see where is the Hubble Telescope pointed right now. And at that time, they had a little label saying LIGO binary neutron star. So even though we were trying to keep it quiet before we actually confirmed it, the Hubble Space Telescope broadcasted the discovery to the whole world. That's all right. Those things happen. But the thing is that then the Hubble Space Telescopes and almost all the other radio telescope, infrared telescope, etc. in the world were able to find this new light. And what that is the big cloud of super hot gas that was produced by this collision. And as you see in the little square there, as time was passing day after day, it became dimmer and dimmer and dimmer. And that makes sense, right? You have a big explosion, you create a super hot ball of gas, and that cools down. But it's even more interesting than that, because astronomers can do studies that are called spectroscopical studies. So you can look at the different components of the light coming from that object, from that cloud of gas, the different colors of light, from the visible all the way to the infrared, so beyond the red light. And every single element in the periodic table has a particular signature. So by seeing the component of the spectrum of this light, we were able to confirm that a lot of the heavy elements in the periodic tables were generating this collision. So quite literally, a lot of the elements that you and I and everything around us we are made of, comes from the collision of 2 neutron stars. So we are pretty much, very likely, made of the remnants of some neutron stars like this. So as you can imagine, all these discoveries were quite important. But before now I move on a different topic, I want you to listen to the sound of gravitational waves. So, first of all, gravitational waves are not sounds because they are ripple, oscillation in space and time, vibration of the universe itself, and they propagate in vacuum, so they're not sound. But our detectors, and I'll explain later how we do that, can hear those gravitational waves, convert them into a signal which is stored in our computers. And it so happens that the frequency, the pitch, if you want, the note of the signals or the gravitational wave signal emitted by neutron stars, they're in the same band of the sounds that we can hear with our ears. So what I'm going to do now is play for you the gravitational wave signal of those two neutron stars that collided about 150 million years ago, travel across the universe. We detected them with the LIGO detectors, and we can convert that into sound. This is almost certainly not going to work, but let's see. Yeah. So this is rumble, is the background noise of our detector. Then as time passes, as shown by this white line, you see that there is a streak getting brighter and brighter and brighter, moving up in frequency. Remember, the two neutron stars will get closer and move faster and faster, so the frequency will increase. Now you see it quite clearly. That's the signal from the gravitational waves from those two neutron stars. Near the end, you will hear it. Listen very carefully. Very faint, but you heard that whoop, and one of our people here was very good earlier to do that impression, so maybe we should call him again and try to do it again. But so this is literally the signal, the gravitational wave signal generated by those two neutron stars that made the entire universe vibrate like that, and we finally were able to detect them and convert them into sound for you to hear. I think this is quite remarkable. Other people also thought that this was quite remarkable. And so the discovery by the LIGO observatories were awarded the Nobel Prize in Physics in 2017. As always, the Nobel Prize doesn't go to collaboration or project, but goes to people. In this case, went to Rainer Weiss, Barry Barish, and Kip Thorne, the three founding fathers, or three of the four founding fathers of the LIGO experiment. The fourth one, Ron Drever, unfortunately passed before they could award the Nobel Prize. One of their rules is that they cannot award the prize after somebody died, unfortunately. So all three of them are very much active, very much interesting personality to meet and get to talk with them. So at this point, you all have probably this question in your mind. So, all right, you showed off gravitational wave signals. You told us at the beginning that this change in distance is more than the size of a proton. How is that even possible? How does LIGO detect such small signals? Well, we use an instrument which is called a Michelson laser interferometer, which is a very complicated word for something like this. So a laser is essentially a source of light wave. So we have a laser that creates this light wave that is sent to a mirror, you see there in the center. That mirror is called a beam splitter because it splits the laser beam in two parts. One will travel 4 kilometers, 2.5 miles in one direction, and reflect back. And the other one will travel 2.5 miles, 4 kilometers, the opposite, in the orthogonal direction, and come back. If the two distances are tuned properly, then the two waves coming back, one will go up, the other will go down, they will sum to 0. It's called destructive interference. But then if a gravitational wave comes by, one of the two arms will get a little bit longer, the other a little bit shorter. So the laser going in one direction will take a little bit longer to come back, and the other will come back a little bit earlier. So they won't cancel each other anymore perfectly, and so some light will leak out. This is how a Michelson interferometer works. It converts change in distances due to the gravitational wave signals into a fluctuation of light. Then we can put a detector there that converts that light into an electrical signal that eventually gets into our computer. Sounds easy, right? Simple enough. No problem. But the problem is that when people almost 3 decades ago figured out that this was a good idea, and by the way, this is the most sensitive instrument we have invented so far to measure small changes in distances. The problem is that if you want to get to the level of sensitivity that is needed to detect gravitational waves, this thing, with the best of the technology we had even today, would be 1,000 times less sensitive than what we need. So how do you do that? Well, the longer, the bigger the instrument, the more sensitive it is. And the higher the laser power, the more sensitive you are. So why don't you make this, instead of 4,000 kilometers long? You can imagine that, considering that Earth isn't quite as flat as shown there, or as some people might believe, making something 4,000 kilometers long could be a problem. How about more powerful lasers? Well, at the time, and even nowadays, we don't really have lasers that are powerful enough. So, brute forcing an approach out of this didn't quite work. So what we had to do is to be a little bit more clever. And so this complicated scheme here is actually, believe me, a very simplified scheme of how our detector is built. But you will recognize two things. On the left, there's a laser, that little box, black and red with the label laser. So, and then you see the laser goes to a beam splitter, which is at 45 degrees in the center. And then there are the two orthogonal perpendicular arms of the detector. So the beam will go 4 kilometers in one direction and 4 kilometers the other. But instead of making it simple, like I explained or shown the animation before, at the beginning of the 4-kilometer arm, we add another mirror. What that mirror does is makes the lasers, the photons in that arm, going back and forth about 300 times. In that way, we essentially virtually make the arm 300 times longer. So instead of having to build something which is way too big to fit on Earth, we use this kind of trick. That comes with the complication of having more mirrors. But you know how the things go. When you add 2 mirrors, why don't you add a few more? So if all the laser doesn't go to our main detector because we have destructive interference there, it means that that laser needs to go somewhere, and it goes back toward the input. So we decided, and you see it right there on the left, to add a power recycling mirror, which does exactly what the name tells you. That power, laser power that would be otherwise wasted, is recycled into our instrument. And we managed to take those photons and send them again inside our instrument about 50 more times. So practically, we increased the power of our instrument by about a factor of 50. So instead of having to build a Death Star, we can just add 1 mirror, which is not as expensive as the Death Star. So I think that was a win. And also, the Death Star never really worked very well, so we shouldn't do that. And then, as you might notice, the one more mirror, which is called the signal recycling mirror, because one says, well, you're recycling the power. Why don't you recycle also your signal? And it turns out that actually is a good idea, and you can put a mirror just before the output and send back the laser again to accumulate more signal, and so make it even more sensitive. So, but this is in theory, this is on paper. How does this thing actually look in reality? It looks like this. This is a flyover the main central building of our detector in Washington State. So you see those 4 kilometers concrete tube that protect our laser. And now you see we switch to Louisiana. You can see quite the difference of landscape from the desert to the woods and the swamps there. So in that building there's the laser and the beam splitter. And then the laser propagates 4 kilometers, this is an animation, 4 kilometers inside a steel tube that is inside that concrete tube, and air has been pumped out of the steel tube. There's a vacuum there. So the laser will move 4 kilometers one direction, 4 in the other, bounce back, and you can see some real footage of how our instrument looks inside that main building. All those big tanks contains our instrument and contain essentially no air. And the reason is that air would be a problem for our instrument, limitation of our instrument. Now, one more question you might have is, why 2 observatories? Why not 1? Well, unlike almost any other astronomical observatory, our instruments are omnidirectional. They can detect gravitational waves coming from any direction in the sky, which is great. You don't have to point a 4-kilometer long thing, but it's bad because with a single detector, you cannot tell where things are coming in the sky. So we do a thing called a triangulation. So we measure the very slightly different time of arrival of the signal at the 2 detectors, and that allows us to point in the sky. Might seem a very complicated thing, but actually your brain is doing that right now. Because even if you close your eye, you can tell if I'm in the center of the room, or if I'm moving to the left, or if I'm moving to the right. And the way you do that is the brain takes the little different time my voice arrived to your 2 ears, and then from that difference, the brain can tell if I'm on your right or on your left. So nothing really new. Nature often invented things way before us. And of course, there's a lot of other complicated and advanced technology in all we do. For example, I already mentioned that our mirrors and all our instruments are in vacuum, and the reason for that is twofold. One is we don't want any dust, any contaminant, anything going in and pollute our mirror. Whenever we work on that, we have to repump the air inside our vacuum chambers, and then we dress up in what is called a bunny suit. If you've seen some of the movies when there's somebody in a hazmat suit, it's a similar thing. But in that case, it's not to protect us from what is in the instrument, it's to protect the instrument for the dirtiest thing around there, which is us. So that's why we have to dress up in complete cover suit and everything like that. Because our mirrors, you see them at the center, the core optics are big pieces, they're 40 kilograms, 90 pounds each, of fused silica, which is a fancy name for very high quality and very expensive glass. And we couldn't have them just sitting on the ground, because the ground, even now, vibrate about a millionth time, as a million of millions times more than what we're trying to detect. That's why they need to be suspended with very complex, sophisticated seismic attenuation systems that make it possible for those mirrors to move much less than anything anywhere else on Earth. Quite literally, our mirrors, the LIGO mirrors, are the quietest place on Earth. Only going out in space would make them move less. And with that, okay, so before we finish, the way we work essentially is that we build our detectors, we design them, we build them, and as you can imagine, they didn't work. Because the first time you build something, just doesn't work. So we go through a phase which is called commissioning, that we scratch our head and say, why aren't you working? What can we do? And eventually we solve some of the problems and we get our detectors to a certain sensitivity. Once we are good enough, we say, okay, let's stop fiddling around with the instrument. You take all the physicists and you go out of the room, because now this is an observatory. Now this needs to be turned on and detect gravitational waves. When we do that, we call it an observing run. And we had 4 observing runs so far, 3 completed and 1 ongoing, going from the time of about a few months to several years. So during the 01, 02, and 03, I know physicists are not that, there's not a lot of fantasy, so we call them 01, 2, 3, 4. We keep going until we finish numbers, I guess. During the very first, the 3 observing runs, the 2 LIGO detectors saw 90 signals coming from the collision of different objects. And you see them in this graph here. So time is sort of passing on the horizontal axis, and the vertical scale tells you how big in solar masses of our sun, how big the objects were. And you always see there are 2 little blue dots with arrows going up to a bigger dot. Those are the 2 black holes that merge into a bigger black hole. And you see the biggest one up there, almost to 200 solar masses, and the very last one, the big above 100, was the one that David was referring to earlier. So this is interesting because observing those black holes that big, when we know that stars that big cannot exist. So those black holes cannot come from a star that goes supernova. They must come from smaller black holes that merge and merge and merge until you get to bigger black holes. So this was quite a lot of discoveries in the first 3 observing run. Now, the LIGO detector is now in the middle of what we call 04, the 4th observing run, that started in May last year and will continue till June of next year, about 2 years total. And in that first part, so in a little bit more than a year, we detected 118 more events for the collision of black holes. Why so much more? It's because we made our detectors more sensitive. The more sensitive they are, the farther away in the universe you can go, and the more stuff that collides there is out there. So far, we have detected more than 200 gravitational wave signals from the collision of black holes and neutron stars. So that's quite a lot of discoveries if you think that the field of gravitational wave astronomy is not even 10 years old. So a lot of discoveries came, a lot more will come in the future. So I invite you to stay tuned, because a lot more interesting discoveries will happen. And with that, I'll leave you with this final slide, where there are some pointers for those of you that like going on internet, Twitter, X, whatever it's called now, Facebook, all of that. You can find a lot of information, more information. There's pointers to 3 very nice short documentaries that can explain everything much better than I did. Thank you for your attention, and I'm happy to, well, back to David.
Yeah. Bill, you want to grab a couple chairs for us? Yeah, we'll take some questions here. We're going to grab a couple of chairs and we'll sit down, and we have some time to take audience questions. I have a question for you first. What will it take to find colliding supermassive black holes? Because I see that we haven't seen any of those yet with the detectors.
Yeah. So the reason we haven't seen any bigger black holes is that the bigger the black hole is, and the slower they will move around each other. Makes sense, right? They're big, they go slower. But so if they go slower, it means that the gravitational wave signal is at lower frequencies. So now on Earth, unfortunately, we are limited by the vibration of the ground. We cannot push our sensitivity too much below 10 or 20 hertz, 10, 20 oscillation per second, because the ground is moving so much, there's nothing we can do about that. So to detect supermassive black holes that will be a very low frequency, we need to go to space.
Okay.
And we are going to space, not me personally, but the LISA project, the Laser Interferometer Space Antenna, is the same idea as building a LIGO detector. And if you thought that building LIGO was crazy, the LISA instrument will be 1 million kilometers in size. So can't quite fit in orbit around Earth. It will be in an orbit around the sun, in one of the trailing points of the sun.
Interesting.
That's a project funded by ESA and NASA and should be launched in 2036 or 34. I don't remember exactly, but so in a decade or so. But that's going to be exciting.
It will be. Well, let's have a seat. I'm going to sit here, and you can have a seat here, and we'll. I'll ask you a few more questions, and then we'll turn to our audience. So, what is next for LIGO? Right now, the run. When will this data run that's happening now? When will we get to see all those black holes that have been found?
Yeah, so right now you can actually see in real time the discoveries we do, because now everybody, any of you can download an app on their phone and have an alert when there is a gravitational wave candidate from LIGO. So we make our discoveries public right away, within maybe 30 seconds from the discovery. What comes next? Well, as you can imagine, I'm an instrumentalist, so I like to design and build those instruments. So even though now LIGO is working pretty well and taking amazing data, I am already working hard with all my team to make sure that we have upgrades ready to go. June 9, the observing run will stop, and all of us will be ready to jump to the detector and take things out and put new and better things in. And after that, we already know what kind of improvement we're going to install in 10 years from now. Beyond that, we are thinking of a future detector, which is called Cosmic Explorer, that will be 40 kilometers long, 40. So 10 times bigger than what we have now. We call it Cosmic Explorer because it will be so sensitive that it will reach so far in the universe that it will detect all the collision of black holes and all the collision of neutron stars, because if you go farther away, you go back in time, and there weren't stars to form neutron stars, or there weren't stars to form black holes. There might be primordial black holes.
What's the rate at which you'd expect to be detecting those collisions if we're hearing every collision, or detecting every collision? You don't really hear them. But if we're detecting all, would it be like 1 every 5 minutes or something? It seems.
So right now, we are detecting 1 collision of black holes every 2.5 days. So if in the next 5 years, we expect to make our detector, let's say, 3 to 4 times more sensitive. So if you reach 3 to 4 times, let's say 4 times farther in the universe, it means that the volume is 64 times that, right? So the rate will be 64 times. So we're going from an event every couple of days to one every hour.
Every hour, okay.
Roughly.
That's amazing.
When we get to the point of having Cosmic Explorer, some of my colleagues that work on the data analysis, they're worried that the signal will start to overlap to each other.
Yeah.
And the problem then would be that one signal we will not have time to finish before another time is on top of that.
Right. So I think the way to disentangle those will be to use the multiple observatories, because they will be entangled differently for each of the observatories.
That's one way of doing it, yeah. But depending where the observatories are, you get different time of arrival and different also waveform due to the different polarization of the signals.
Yeah.
But it's a good problem to have, right?
Well,
to have too many signals. That,
yeah.
And I like to say that my job is to make the data analysis people life much harder.
Yeah. Yeah. Well, I remember attending it was an American Astronomical Society meeting, probably in maybe 2010 or something, and they were very excited about it coming online, and they were confident that the work maybe you had been doing to bring it up to where it is now was we were going to start detecting gravitational waves. So it used to be none. In fact, it was running for a while, and it just wasn't sensitive enough, if I remember correctly.
That's correct, yeah. The first iteration of LIGO, that now we call it initial LIGO, at the time we only call it LIGO, of course, was not sensitive enough to detect a gravitational wave. The amazing thing is that we knew that. And the National Science Foundation, which is the US government body that funds fundamental science, they agreed to fund initial LIGO with quite a lot of money, knowing that that was pretty much a prototype, just the first stepping stone toward what we call now advanced LIGO, which is what we have now. That was the instrument we hoped would be sensitive enough to detect gravitational waves.
Well, fantastic stuff. I can't wait to see what's coming. Well, let's turn to our audience here and see if we have any questions here. Yeah, right here.
How do you precisely measure time, and what are the engineering challenges in measuring time in these detectors?
So the question, I'm going to repeat it for our folks that are watching the stream. The question was, how do you measure time, and how do you track that for the detectors?
So surprisingly, measuring time is one of the easiest things for our detectors, because the only reason we need to measure time is to make sure that we can measure exactly the time of arrival of the two signals to detector. Now, the two detectors are about 3,000 kilometers apart. So at most, since gravitational waves travel at the speed of light, the difference will be 10 milliseconds, so 10,000th of a second. So the way we do it, all our electronics is synchronized to GPS clocks. We have atomic clocks on site that are synchronized with GPS satellites. And that's more than enough to get better than a microsecond accuracy, which is that's all we need for this kind of measurements.
Interesting. Over here.
Yeah, I'm just, first of all, totally in awe we managed to do this, so props to you guys.
Thank you.
So as we generate this data and are discovering all this, what is that data feeding? I mean, what are we validating models of the universe, or how are we using that data?
Yes, the question was, we're getting all this data on the colliding black holes. Now, what is it being used for? Is it validating theories of universe? Where is it going? What are we doing with it?
That's a very good question. So far, what we did is to verify that the two black holes, they produce a signal which is exactly as predicted by the theory of general relativity that explains how gravity works. So that's one very important information, because it tells, okay, it's an experimental way to verify that the theory is correct. With the collision of two black holes, we have information about what happens in nuclear matter at that density. We have no other way to confirm that. So we can learn how actually stars behave when they are that dense. Looking at the distribution of the sizes of the black holes, we actually have a very important information of stellar evolution. We can learn how stars are born, how they evolve, how they die, and all of that. What I find the most interesting thing, although, is that there's this thing called quantum gravity. Some of you might have heard of that. The problem is that quantum mechanics is a physical theory that explains the very small things, like atoms, subnuclear particles. General relativity and gravity is what explains very big, massive things. The two theories speak a completely different language. People have been tried ever since the 50s to put them together, and we have failed. But where is something that will be at the same time very small and very massive? That's a black hole. So by studying the collision of two black holes, that will be the only way, in my opinion, to find evidence of what is this quantum gravity. Because how did we learn how the atoms and the subatomic particles behave? We build particle accelerator. We smash protons or electrons together, and we see what comes out. Luckily, or unluckily, I don't know, we cannot build our own black holes and smash them together, but the universe is doing that for us. So what we're doing is trying to discover how fundamental science, quantum gravity works by looking at what happens when the black holes collide.
I've thought of another question, so I'm going to take my leave here and go ahead and ask it. do we have any capability to see if there's anything to stop the collapse of the black hole? A lot of folks, myself included, are a little uncomfortable with all the mass going down to a single point. This leads to, well, problems, singularities. If there were something in the universe, we don't know what that would be, that could stop that collapse. You could still make a black hole. You just need to get the thing dense enough. So do we have any capability in the signal to see whether these things are truly points or whether they have some physical size?
Hopefully, eventually, yes. So if general relativity, our theory of gravity, is actually correct, then I'm sorry, those are really points.
Well, exactly. It's uncomfortable, but it's
which
true.
Which is comfortable, but hey, I think Einstein said that the universe has no obligation to make sense to you, right?
It doesn't care about my feelings.
But then my hope, honestly, is that at some point we will detect stronger signal, more and more signal, and we will see that, hey, there's a little deviation. The signal we saw doesn't behave the way Einstein predicted. And then we say, yes, finally, because that's the best thing for a physicist, a theory that finally starts to crack. Because you have a little crack in the wall, and you can peer behind the wall and see what lies behind. Yeah. So maybe they're not points. Maybe there's something weird that happened on the event horizon, those black holes. Yeah. We don't know, because there's as many theory as there are theorists. Mm-hmm. And we don't have, at the end of the day, there's only one universe. Maybe. We live in only one universe, let's put it that way. And so the universe is right. There's only one correct answer, and we need some experimental evidence that we don't have. Yeah. But hopefully we'll have it.
Excellent. They're in the center, and then we'll come down to Alan.
Wasn't there a third observatory being built?
Yes. So there is a third observatory called Virgo, which is a European collaboration, which is in Italy. Incidentally, is where I got my PhD, and I worked there for many years. They finished building it, and it reached a sensitivity which is about a third of the LIGO detector. So it's still important, and it's actually now working together with us. There's a fourth observatory being built in Japan called Kagra, which is an underground observatory. So that's a little bit more sophisticated, but they're still working to make it more sensitive. And we have all packed up a third LIGO detector, all the components for a third LIGO detector that we will be built in India. So the India government have an agreement with the US government to acquire the land, provide infrastructure, and we will put our instrument in there.
Yeah. So yeah, Alan, and then we'll go back there.
I have a personal question and a question from YouTube, if that's okay.
Yeah.
A personal question is, now I forgot it, so I'll do the YouTube one first. Oh no, I remember my first one. So between observational runs, do you ever leave one of the detectors on? Like, are you afraid you're going to miss some unique event? Or do they both shut down at the same time? That's my question. And then the YouTube question is there a special team that works on finding out ways to make these instruments more, more precise, more powerful? Like, is there a special team that's dedicated to that?
Yeah. So the questions for the folks at home, sorry, I've been forgetting to say it, is do you shut down all the detectors at once, both the instruments, or just one at a time? And then the YouTube question was, is there a team of people that specialize in the upgrades and making the detectors more sensitive?
So to answer your first question, yes, we shut down all the detectors at the same time because it is really important to have two detectors running at the same time to be able to localize in the sky where the signal is coming from. By having only one detector, we would miss the information of where in the sky it is. So if we were to see the collision of two neutron stars coming from only one detector, we were not able to tell the astronomers, hey, point your telescope in that position. So that's why we decided, then not knowing when the signals are coming, any time is as good as any other because they're random, right? So that's why we shut down both of them. To the question from YouTube Online, yes, there is a team. And if you remember when David introduced, said that I'm the deputy head of system science and engineering at Caltech. The system science and engineering group is the group mainly based at Caltech with people also the two observatories at MIT. We are responsible for coming up with smart or crazy, it depends how you feel, ideas to improve the detectors more and more. That's why I was saying earlier, now the detector is working and our team is busy building already the parts that will go in a year. And it's also busy designing the parts that will go in 5 years and busy collecting ideas of what we're going to do in 20 or 30 years from now. So yes, there is a team of engineers and physicists that do that. As you can imagine, we have all kinds of expertise in this. We are not only physicists or scientists, but there are mechanical engineers, electronical engineers, vacuum engineers, even civil engineers, because you have to build a 4 kilometers long thing. That takes some construction.
Yeah. Now, is there a reason it looked like the lasers were using wavelength that was over 1,000 nanometers? That feels long to me. That's in the infrared, I think.
Yeah, that's in the near infrared, so it's not visible and with our human eye. The reason is that those are the best, most stable, and most powerful lasers that have been developed mostly decades ago to use in telecommunications. Now telecommunication they don't use that wavelength anymore. They move to longer wavelength, but still, those are the most powerful, stable, and precise lasers that we have.
Great.
Originally, the first idea was to use argon lasers, that are the big tubes with argon gas and big sparks inside, and those were terrible lasers. So luckily, a better technology came along, because those would break down continuously.
Yeah. Excellent. I think you had a question. Yeah.
Okay, so a question about particles versus waves. We're all talking about waves, so the elephant in the room, does the math lend itself to there being a particle? And is there an observer effect? If you're looking at this gravitational wave, does it only exist because we are looking for it? Or has it always existed and is a particle also?
I'll try and translate your question a little bit for our at-home audience. The question was, we've been talking about these as waves. We have the lasers, they're being combined. The interference is a wave-like phenomena. Do you see any particle-like phenomena if we look at it? And then the fact that we're observing these, does that affect the experiment at all? As we've all heard about quantum mechanics, when you observe something, you can collapse the wave functions, you can change things. So does that have any effect?
So gravitational waves are, in the parlance of quantum mechanics, a classical phenomenon, because general relativity and the theory of gravity is purely classical. There's no quantum mechanics there. And what I mentioned earlier is that quantum mechanics is a theory that we know how to use to explain small things, but we don't have a quantum explanation of gravity. So there isn't a theory of quantum gravity. We don't know. So if we believe, as most physicists do, that quantum mechanics is a fundamental language of the universe, then yes, at some point there should be such a thing as a graviton, the particles that correspond to gravity. That's not something we will observe with the gravitational waves, because it's like looking at a light bulb, right? There's so many photons that they don't behave in a quantum mechanical way. So we will not observe quantum mechanics effect in the gravitational waves themselves. My hope is that we will be able to observe quantum gravity effect in the behavior of the collision of the black holes.
Excellent. Interesting. Any other questions? Yeah.
When you have two of these immense objects rotating around and finally coming together, is the energy being radiated out in a plane, or is it kind of more in a sphere? And when you observe them, do you have to be in that plane if it's going out as a plane? Or if you're out of that plane, would you maybe miss it?
Yeah, the question was, these black holes merge, the radiation that comes off, is it given off in a plane or does it come off spherical?
So it's not quite in a plane. It's not quite spherical. Of course, things are always more complicated than that. But if the two black holes are orbiting in a plane and you are looking from the top, then that's the position where you wouldn't get any gravitational wave, right? If you're in the plane, you get most of it. If you're in between, you get something in between. So luckily for us, we don't need to be exactly on the plane. But of course, if you have, depending on the inclination, you can get more or less gravitational waves, more or less strength.
We may be missing some events.
We are definitely missing some events because they're not well oriented, because they happen, even our detectors, I said that they are sensitive to signals coming from any direction. But that's not quite true, almost. But there are some blind spots. So if a signal would come from that blind spot, we would miss it. And we know that we miss a lot of them because they're too far, and the blind spot or the orientation is not optimal. But what can we do? The universe doesn't agree of aligning all of them in the right direction for us, of course, right?
Here in the front.
Yeah, so I had an opportunity to speak with you a little bit before the show, and so we started this topic, but will LIGO be useful in studying the very early universe, even the Big Bang itself?
The question was, is LIGO useful for studying the very early universe, including the Big Bang?
So not quite LIGO, because it will never be sensitive enough. We hope the future gravitational wave detector will be. And the reason is that at the very time of the Big Bang, well, maybe 10 to the minus 34 seconds after the Big Bang, but close enough. So at the inflationary period, our theory predicts that there's a lot of gravitational waves will be emitted in the form of a cosmological background, like the cosmological microwave background that happened about 30,000 years after the Big Bang. There is an imprint of gravitational waves of the Big Bang itself in the universe. The point is that it's extremely weak. Even the most crazy, I shouldn't use crazy, the most complex, optimistic, thank you, the most optimistic theories tell us that we are probably not sensitive enough to detect that by a factor of 100 or more. So we will need to improve our detector quite a lot. So maybe Cosmic Explorer will be able to see that, which is the future 40 kilometers long detector, or maybe LISA, the space antenna, or maybe we'll need to invent something even more sensitive. But eventually, we know that there should be a gravitational wave cosmological background, and seeing that would be definitely one of the few ways to see what happened almost right at the Big Bang.
Yeah.
Now, will that background be greatly different depending on, say, the Hubble constant, things like that? Will you be able to measure that? Right now, there's the tension between the Hubble constant. Locally, we use supernovae explosions, sort of locally, but the cosmic microwave background radiation is used to get a different number, and they don't agree. So what do you...
So luckily for us, we will be able to say something about that tension before we need to detect the cosmological background in gravitational waves, because when those two neutron stars collided, we were able, from the gravitational wave signal, to measure the distance. And the astronomers that found it in a galaxy were able to find which galaxy and to measure the redshift of that galaxy. So gravitational wave detections are a complete new and independent way to measure the Hubble constant, which is the rate of expansion of the universe. So for now, our measurement has still an uncertainty which is larger than the difference between the two measurements. But the more signal we see in the coming 5 to 10 years, that's my prediction, that's my guess, that's my hope maybe, we'll be able to narrow that uncertainty and see where our measurement lands. Very likely it's smack in the middle, and then we'll have to figure out why.
Yeah, it's always fun when that happens. What are you most excited about with LIGO? What's your next, what do you think about in the morning when you wake up that you want to go do with your instrument?
Well, so I think I have two answers for you on that. One is the thing that I find the most exciting about my job is to find ways to make this instrument most sensitive by tuning what we have already installed, tuning our software, our control systems, all of that, or by finding new materials or new technologies that we can in the future install to improve the instrument. Being an experimental physicist and instrumentalist, that's what excites me. On the pure science point of view, what I find will be the most exciting thing is when we will start, as I mentioned earlier, seeing that the collision black holes, they don't behave the way that is predicted by Einstein, but the general theory of relativity, because then we start seeing something new. And there's nothing better than seeing something new in the universe that your theories cannot explain.
Yeah, it's absolutely fascinating. Incredibly interesting, this opening up sort of the dark universe to us. We've been observing using photons, using light, learning about the universe that way. LIGO has opened up an entirely new way to explore and observe the universe, and it's just super, super exciting. So let's all thank our guest again, everybody. Thank you so much.
Thank you.
Next month, we're actually going to talk about some of these things that are, well, we're finding things with the James Webb Space Telescope that don't quite agree with the standard model of the universe. Folks like to think, oh, we know how everything was made. This is when massive black holes should show up. This is when galaxies should be made. Well, there are observations that are coming out that don't quite agree with that. We're going to be talking about that next month, so join us next month at All Space Considered on the third Thursday on YouTube. We will not be in our theater here. Don't come up for the show. Our Leonard Nimoy Event Horizon Theater is undergoing a renovation. We're going to get some new projection equipment, some new equipment in the control room. Eventually, the whole theater will go under renovation for several different stages, but we're going to be closed a little over a month. So All Space Considered will happen, but you'll have to watch it online. If you're a foundation member, watch your emails maybe. We might have an opportunity for you to see it in a different way. We'll see. But we'll come back in September, hopefully be in person if everything goes right with the theater. But thank you, everybody, for joining us. I'm Dr. David Reitzel. All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of Los Angeles, and of course, we always like to thank Griffith Observatory Foundation. They're our exclusive nonprofit partner, and they're the ones making this renovation of our Leonard Nimoy Event Horizon Theater possible. So let's make sure we thank them. And thank you, everybody, for joining us tonight.